South Pacific, EE392 unit, Thursday lab session group. Project team is myself, Tima, Kartik, Sayasin, David, Dayang, and Shishil. And this is a recording on the 13th of October 2017. Our signals, audio files that were given for analysis is S1 up to no, this one. The wave audios S4, S5 to S9, and our codes. This is in order. Pre-filter spectrum 392 generated. This is the filter that's generated, and post filter for comparing signal before and after using the filter. And the pre-filter, we've decided to use S5 wave audio because it's the clicks are very clearly represented when I run this program. That's the audio info file. We have sample rate 44100 there. We have a total of samples 24696 and runtime is 0.56 seconds. This is the original signal that was given, S5 wave signal, and we use this, the first click for analysis. From this first click there, you can see here this figure 2. In our plot, we have here from 1323 somewhere on that to 2100, and that's the length of our new sample that we are analyzing. From here, we need to get our frequency plot to get our fundamental frequency for our filter. So that's what we have done here. We use FFT. Because FFT instead of DFT, it filters out noise faster than the DFT, and DFT there'll still be some noise left, but the FFT is efficient in that manner. And our plot, as you can see here, this is our new sample that we're using for analysis, and our frequency plot is this one. Power spectrum plot, and we have our first spike. This is we've taken this as our fundamental range, where our range is, and yeah, let me just zoom in this range. This is where we've used our frequencies to design our filter, and in this range we see that our spectrum, the frequency is below 5 kilohertz. So we use this spectrum plot to prove that it is really below 5 kilohertz, our range for our fundamental signal. So let's run this one here. And it should show the frequency plot similar to the instead of just graph, it will show a spectrum signals. Okay, while that's running, we have a generated model here. Is from the FD, filter designer function. This filter FDA function is from the apps, as you can see here. Yeah. When you go to apps, drop down arrow, there it is. Right. Drop down arrow, you'll go down to filter designer. When you click on this, you'll get the other window. filter designer is this window. This is where you design all your filters. Okay, and back to spectrum, and here we have our power spectrum. Our frequency here, you'll note 5 kilohertz is here. Before that is our fundamental, the range where our fundamental frequency is. Let me just make it more clear. There. So 5 here, we are only using this range here. Right there. There. So this validates that our plot, frequency plot, this one, is correct. So from here we use it for our bandpass filter. We choose bandpass because we need to allow certain range of signal and remove all the rest of the other signals. So we put our sample here, 3200, that's here around about this area, and 38 is our pass frequency somewhere here. 4200 is somewhere around here, and 4800 is close to 5000 here. Set. And we've used our attenuation. Let's see. When I go to FDA here, you'll see that I used 202. This is from research. According to research, decibels for dolphins are around 202 decibels, 210, 220. So we've chosen 202 in this case. And here we've chosen bandpass. We're doing equiripple FIR filter. And after the design, this is what the filter looks like on top. So here, this band here, this is allowing this signal to pass under this band. Beyond that, all other signals will not pass. Okay. So from here, this filter generated, then we go to our post filter. So let me just close all these other images. Close this one. Okay, our post filter, we have here, this is our S6 wave. We want to test the S6 wave using our S5 analysis. We've been using S5 to get our fundamental frequency range. So this basically means our fundamental frequency lies between these two pass frequencies, between 38 to 42. So in our post filter, we used S6 to test. Read for the S6. We have this here. This is generated. This is the filter from this tab, and we have the range. We need a FFT for frequency plots, power plots. Yeah, as you can see here. This here I've commented the sound because if I don't, whenever I run, you'll hear the sound. So I'll hold it back for now. And figure 2 is the plot of both pre-filter and post-filter stuff. Let me just run this one. Here. So this is our S6 wave signal. As you can see here, pre-filter is this is in frequency domain, normalized frequency for Nyquist frequency, and this is we've taken it back to sample display, sample domain. And we have the original signal for blue, and the filtered signal is the red one. And here, as you can see, this is what the signal frequency frequency that we allow. We've changed all our frequencies to a Nyquist frequency. We've normalized our frequencies. Okay, so let me just close this. If I change this to S5, back to S5, just to see the filtered and the unfiltered signal, the plot. So we have clicks instead of just noise. Okay, and that was our project. We have 4 files. Spectrum is used to prove our frequency band is correct, so we can enter it into our filter generated through the FDA app. This one. This you can find under MATLAB apps filter designer. And that's it for Dolphin project. So our frequency is 42 plus 38 divided by 2, which is roughly around 42, yeah, plus 38 divided by 2. So we've put it at 4 kilohertz.
Yeah.
4000 hertz. So that's our fundamental frequency for this project, Dolphin project, which we have done semester 2 of 2017 in the University of South Pacific, FSPE. Thank you very much.